Hello and welcome to the third lesson on electricity. So in this lesson specifically we'll be looking at Ohm's law. I am your presenter, Alex Nkumbi. So quickly let us go through our lesson outcomes. Alright, so during this lesson or in this lesson you will be able to describe an experiment to show the relationship between voltage and current through a metallic conductor. Then you will interpret the graph of current against voltage or voltage against current. Then you are going to state Ohm's law, and then finally you will describe the difference between ohmic and non-ohmic conductors. At the end of this presentation you will do an exercise that involves a question that was extracted from a Zambian past paper. Alright, so with these lesson outcomes set, we straight away go into our first part to describe an experiment to show the relationship between voltage and current through a metallic conductor. Okay, so the diagram, the figure here shows the experimental setup. We have a 12 volts battery in this case, and to this battery a resistor is connected. And this resistor R is also connected in series with an ammeter, and there is a rheostat here, and there is a voltmeter here. So how does this experimental setup work? First of all, I want us to understand that we are trying to investigate the relationship between voltage and current of a metallic conductor. In this particular case we are using this resistor to represent that conductor. Okay, so how is it done? So in the experimental setup shown above, the resistor R is put in water in order to keep it at almost constant temperature. Remember in our previous lesson when we were talking about resistance, we said one of the effects of resistance is that it causes a conductor to heat up. And if a conductor continues to heat up, then its temperature will not be constant. So since we want the temperature to be constant, the resistor R is submerged in water. The idea here is that since water has high specific heat capacity, it can actually absorb heat from the resistor without actually changing its temperature in a given period, a short period of time. So that's the reason why the resistor R will be submerged in water. Then the voltage or potential difference across the resistor R is changed by adjusting the rheostat. So in short, the purpose of this rheostat you see here is that, by the way, a rheostat is a variable resistor. It's a resistor with the resistance that is not fixed, so we can adjust it. We can either increase or reduce depending on what value of voltage we want. So this rheostat here is used as means of adjusting the voltage across the resistor R. Okay, so that's the purpose of the rheostat R. The rheostat. Then the voltmeter V records the voltage across the resistor, while the ammeter A records the current through the resistor. Okay, so here the purpose of the ammeter is to record the current that is flowing through the resistor. So current will be moving like that, passing through the resistor. Remember, it cannot go this way because a voltmeter is made in such a way that it has very high resistance. So almost we can simply say the current that can pass through a voltmeter is negligible. Otherwise, almost all the current from the battery will pass through the resistor. Okay, so the function of the ammeter is to measure the current passing through the resistor, and we see that the voltmeter is connected across the resistor. It's very important for you to remember this experimental setup. Very, very important, as you shall see later in the question that you'll be answering in your exercise. Okay, so I think I have explained the experimental setup. and how the experiment will be done. Okay, so when we can begin from 0, we adjust the rheostat so that the voltage across the resistor is 0. So we look at what is the current when the voltage is 0. So we read the ammeter A, record its current. We also read the voltmeter V and record its voltage or potential difference. Then we adjust to another value we want. Maybe we go to 2 volts, to 4 volts, 6 volts, 8 volts, just like that. And we keep on reading the ammeter for the corresponding value of current flowing through the resistor. Okay, so that's how the experiment is done. Now let us look at the experimental results that can be obtained from such an experiment. So let me mention here that the values that I have used here in this the table that I'm going to show you are not the values you expect every time, because in another experiment you may not be having 2, 4, 6, 8 as values of voltage you choose. You may be having 0, 1, 2, 3, 4 or any other value, or you can have 0, 4, 8, 12, just like that. So in this particular experiment, so this table here is showing us the experimental results from an experiment such as the one that we have just discussed, which is this one here. Okay, so this table shows us that when the voltage is 0, the current is also 0. And I'm sure you are able to remember our first lesson on electricity. We said voltage, which refers to potential difference or electromotive force, is work done when a unit coulomb of charge is moving. Okay, so if work done is 0, you don't expect current, because current results from the flow of charge. So 0 voltage, 0 current. So when the current is 2.0, when the voltage is 2.0, we have seen that the current is 1.0. When the voltage goes to 4.0, the current goes to 2.1. When the voltage is 6.0, the current is 2.9. When the voltage is 8.0, the current is 4.0. Okay, so this is a typical results you expect from an experiment like that one, using a metallic conductor or a resistor. Okay, so now these values we can now plot them, okay, so that we have a graph. Now there are two types of graphs we expect here. We can plot either a current against voltage graph, where current is along the vertical axis and voltage is along the y-axis, or we can plot a voltage against current graph, where voltage is along the y-axis and current is along the x-axis. So let us look at the first type of graph we can plot using these values here. Okay, so as you can see here, this graph here is a current against voltage graph. So current is along the vertical axis and voltage is along the horizontal axis. So you can see when voltage was 0, current was 0. Now this is how your graph is supposed to look when you plot. The points of plotting must be seen clearly, like you can see here. Okay, so our first point is 0,0 here, voltage 0, current 0. So that's the one we are able to see on the origin here. The next point we have is when the voltage is 2.0, the current is 1.0. Okay, so we can see that when the voltage is 2.0, which is here, the current is 1.0. so there is a point there to show that. Okay, then we go to the next point. When the voltage is 4.0, the current is 2.1. okay, so we go to our graph, we can clearly see when the voltage is 4, the current is 2.1, somewhere there. So we can see that. We go to the next point. When the voltage is 6.0, the current is 2.9. So here we can see when the voltage is 6.0, the current is 2.9, almost approaching 3, but slightly below. Okay, and then the last point is voltage of 8.0 and current of 4.0. Remember, voltage is in volts and current is in amps. So when you are plotting a graph, ensure that your axes are well labeled according to the way the table is indicating. If the table is saying voltage in V, current in A, meaning voltage in volts, current in amps, also ensure that you label your axes in that manner, so you can see voltage in V, current in amps. Okay, so our last point is when the voltage is 8 and the current is 4.0. So these points have been plotted. Remember, plotting is one task. You earn a mark for plotting, meaning showing those points there. You earn a mark. And then, since we are dealing with a metallic conductor, we expect a straight line. So when we draw a straight line, it will pass through, it will pass, and we have to draw a best fit line. We can't follow all the points like this one and that one and then go, then it is not going to be a straight line, it's going to be a curve. We are dealing with a metallic conductor, and therefore we expect that the current against voltage graph is supposed to be a straight line. So it's a straight line, it will pass through some of the points. So it will pass through 0, 0, it will pass through 2, 1, it will pass through 8, 0. It will slightly miss this one and that one. In fact, you can see from the table that these two values were not giving us exact values. So this could be due to experimental errors, because you can't do an experiment perfect well like a computer. So that's the reason why our graph, since it is expected to be a straight line, it is slightly missing that one and that one. So this is how a best fit line is supposed to come out. If you were given a task like this in an exam, you are given this table of values, you are asked to plot a graph, do not try to use Crookes law, whereby you make this point to be exactly on the line, even that one on the line. No, by that you'll be showing that you are cheating or you are trying to force results. So just plot them the way they are, but instead draw a best fit line. So a best fit line, you will leave some point on the upper part of the line, on the upper side of the line, and on the lower side of the line, like you can see here. So that's our graph of current against voltage. Okay, now the same table here can be used to draw a voltage against current graph. So in terms of a voltage against current graph, this is what we are going to get. So this time we have voltage along the vertical axis and we have current along the horizontal axis. So you can see here, when voltage is 2, current is 1. That's the point. First of all, we start from the origin. When the voltage is 0, the current is 0. Then the next point is that when the voltage is 2, current is 1. So we can see when the voltage is 2, current is 1. The difference between this graph, the voltage against current graph, and the current against voltage graph, lies in the where the two quantities are plotted in terms of the axes. So you can see voltage is plotted along the vertical axis, which is also called the y-axis, and then current is plotted along the horizontal axis, which is also called the x-axis. Okay, so otherwise the procedure is the same like I have already mentioned in the above graph. So you have your values and you draw a smooth line straight with the head of a ruler, line like that. It should be well labeled, and you can see the scale is good. Data must be spread. You cannot have your graph from 0, then 1 here, 2 here, 3 here, then it ends there. No, that would be too small. So you need to spread it like the way this one is looking or the way this one is. Okay, so we can draw those two graphs from the data given. Now, after looking at this graph, we can now proceed to look at Ohm's law. From here, from these graphs, what is it that is coming to our mind? What conclusion can we make? So we go to Ohm's law. Now, statement of Ohm's law can be drawn when we look at the results in the table and also the two graphs that we have obtained, the current against voltage graph and the voltage against current graph for the same information. So from the experimental results, it can be seen clearly that when the value of voltage is increased, the value of current also increases. Okay, so let's see if that is true. So according to the way the line is rising, we can see that when the voltage is increasing, the value of current is also increasing. That's the reason why the line, the graph is rising like that. Okay, or if we use the other graph, we can still see when the voltage across the resistor is increasing, we can see that the current is also increasing, and that's why the graph is rising like that. Now, one thing that we must know is that, and this what we are talking about, whereby when the voltage is increasing, also the current is increasing, is only possible when we keep the temperature constant. And that's the reason why from the onset I said the resistor is put in cold water, so as to, in water at room temperature, so as to allow it to absorb the heat from the resistor, and without that water significantly changing its temperature, because we know water has high specific heat capacity, so it does not easily change its temperature. Okay, so from there we can now make a statement that is called Ohm's law. So the voltage across a metallic conductor is directly proportional to current through a conductor, or to current through it, provided the temperature is kept constant. So the voltage across a metallic conductor is directly proportional to current through it, provided temperature is kept constant. This is what we call Ohm's law. It's very important in your stating of Ohm's law that you do not leave out this part that says provided temperature is kept constant, because once temperature is not kept constant, then voltage may not be direct proportional to current, and the graph may be distorted, may not come out as a straight line that is rising. Okay, so this statement is what we call Ohm's law. This statement here is what we call Ohm's law. So please take note of what Ohm's law is. The voltage across a metallic conductor is directly proportional to current through it. Okay, if I say conductor again here, it may sound like repetition, so let's say through it. Okay, so the voltage across a metallic conductor is directly proportional to current through it, provided temperature is kept constant. This is Ohm's law in statement. Okay, so we move on now to look at different types of conductors. We want to find out, do all conductors obey this law? And what do we call those conductors that obey this law, and those conductors which do not obey this law? Okay, so we have two types of conductors in regards to Ohm's law. We have ohmic conductors and non-ohmic conductors. Okay, so conductors which obey Ohm's law are called ohmic conductors, while those that do not obey are called non-ohmic conductors. So we would like to know which conductors obey Ohm's law and which ones do not obey Ohm's law. Okay, so ohmic conductors include most metallic conductors. So most metallic conductors are actually ohmic conductors. Now take note of the point here, most, because some of the metallic conductors may not obey Ohm's law, such as the filament of a lamp, for example, though being metallic but does not obey Ohm's law, and therefore it's a non-ohmic conductor. So most of the metals obey Ohm's law, therefore metals are ohmic conductors, most of them. And also resistors, like most carbon resistors, they obey Ohm's law. However, there are some resistors that do not obey Ohm's law. Resistors such as a thermistor. A thermistor is a temperature controlled resistor. Okay, a resistor whose resistance is affected by temperature. It is called a thermistor, and in most cases a thermistor reduces its resistance when it is treated to high temperature. Okay, so a thermistor, although it's a resistor, it is a non-ohmic conductor. Semiconductor diodes also are non-ohmic conductors. The filament of a light bulb is also an example of a non-ohmic conductors. Okay, so we must be able to understand what are ohmic conductors and what are non-ohmic conductors. All right, so from here now, let us look at graphs that we can, how do graphs of ohmic conductors look as compared to graphs of non-ohmic conductors. Okay, so what you can see here is the first graph you see here is a current voltage graph of a ohmic conductor. So you can see it's a straight line like the graphs we had in the first case. Like let's look at exactly the graph, the type that is shown. So like this is a current voltage, current against voltage graph. So it's for a an ohmic conductor. So even here it's the same, it's just that it is simplified here, it's just a sketch. Okay, so this is a graph of an ohmic conductor. But look at a semiconductor diode. A semiconductor diode does not obey Ohm's law. As you can see, it's curving. Okay, so this is a graph that is characteristic of a semiconductor diode. It's a non-ohmic conductor. Okay, and we have the filament of a lamp. So you can see it behaves as if it obeys Ohm's law from the beginning, but as the value of voltage is increasing, it looks like current is almost becoming constant. So it curves in that manner. So it means if current continues, it will still be flat because it has curved and almost becoming horizontal. Okay, a thermistor. Okay, a thermistor also doesn't give us a straight line. So you can see there is no proper direct proportionality between current and voltage across through a thermistor and across the current through a thermistor and the voltage across it. Okay, so you should be able to differentiate when graphs are given to you as A, B, C, D in multiple choice questions. You should be able to identify which graph is representing a ohmic conductor or which one is representing a non-ohmic conductor. All right, so we go to our next point. So from the graph of voltage against current, so here we want to focus our attention on the graph of voltage against current. Okay, and this is the graph here. This is the one we are talking about. Okay, so we are saying from the graph of voltage against current here, if we wanted to find the gradient of the graph, you know that the gradient of a graph is found as the quantity along the vertical axis over the quantity along the horizontal axis. In this particular case, what we can do is we can actually we can draw a triangle to help us to find the gradient. Okay, so at any particular point of convenience, let's say at this point, so we can draw a line here. Okay, can draw a line here up to this point. I'm looking at this point also. It's of convenience. Okay, so we can do this. Okay, so we can do this. Oh, excuse me for that. Okay, want to draw another line from that point. Just in a moment, I'll be able to do that. Okay, so we are drawing from this point to that point here. Okay, so as you can see, then we can calculate what amount we have here, the change we have from this point to that point. That will be delta V, because the quantity that we have here is the voltage. So delta means change in. Okay, so we can see that this point is 2 actually on the vertical axis, and that point is 8. So it is 8 minus 2, which is 6. So I'm saying what it means is that to move from here up to there, it is actually 6 steps, because this is 2. okay, and this is at 2. So if you are moving, you say 2, because we don't count these 2 because we are starting from this point. So it is 2, 4, 6. So this is 6, that is delta V. Okay, what about along the horizontal axis? What do we have? This is 1, but we will not count from 1. So we will say we will not count this one. So we are starting from here actually. So we have 1, between 1 and 2 there is 1. So 1, 2, 3 at 4. So we have 1, 2, 3. So there are 3 steps along the horizontal axis, and there are 6 steps along the y-axis. So you can say 6 over 3 and get 2 as our gradient. So that is what we are implying here by saying, from this graph we can say gradient is equal to delta V over delta I, meaning the steps you have moved along the vertical axis over the steps you have moved, corresponding steps along the horizontal axis. That triangle I was drawing can be drawn at any point, okay? Me, I chose to draw it at this point. If you want, you could take it up to here, okay? It means your values will be different. Or you could draw it from this point up to that point. It depends on which points you yourself view as the points of convenience. Okay, so we have our gradient as delta V over delta I. But since our graph is a straight line, and we know that the gradient of a straight line is constant, we should take note of the quantity that is constant between voltage across a metallic conductor and the current through it. And we should realize that the quantity that is constant is electrical resistance. That is what we have just said. I mean, that is what let's look at this. Okay, so let's look at the statement first. So we said the voltage across a metallic conductor is directly proportional to current through it, provided the temperature is kept constant. Okay, and then we came up with a graph, and then we have seen that the gradient of that graph is constant, and that value that is constant is the resistance of the metallic conductor. So we can therefore conclude that the gradient of a graph is equivalent to electrical resistance of a conductor. So therefore, in this formula here where M is, we replace it with R. So R is equal to V over I. And you know, we can work out this equation and manipulate it to make V the subject of the formula, and it becomes V is equal to IR, and this is the one we have here. And we can use this simplified way of making any one of the quantities to be the subject of the formula. So when you cover V, it means you are saying V is equal to I multiplied by R. When you cover I, you are saying I is equal to V over R. When you cover R, you are saying R is equal to V over I. Okay, so basically I think we have come to the end of the points to be covered. Maybe before we just conclude, let's see if we have covered our lesson outcomes. Okay, so we said we should describe an experiment to show the relationship between voltage and current through a metallic conductor. So we did that. We looked at the experimental setup and how it is done. Then we said we should be able to interpret the graphs of voltage against current or current against voltage. So we were able to look at the graphs and we compared the ohmic and non-ohmic conductors. Like we also stated Ohm's law. We described the differences in terms of behavior of ohmic conductors and non-ohmic conductors, and also in terms of their graphs. So it is now time for you to do an exercise, okay? And then after this exercise, an assignment will be posted. Please take note of one point. When you are dealing with a metallic conductor, you expect a straight line. Even if you see that the points that you are drawing, when you are plotting, they don't seem to be falling along a straight line. Draw a best fit line like Ix. As you can see in my graphs here, it's not true that all these points were falling along a straight line, but I had to draw a best fit line, leaving some of the points either up and the other one down, but most of the points were falling along the straight line. Okay, so I think we have covered our objectives, and let us now look at the exercise that you're supposed to do. This exercise was actually question 12, section C, paper 2, July 2016, 5124. This is Examinations Council of Zambia for GCE for 2016. So let me just go through with you. State the difference between electric charge and electric current. So this is not asking you to start defining, no, to say an electric current is this, well, no, that's not what it means to differentiate. State the differences. Okay, that's the first question, and you earn yourself a mark. The next question is, below is a table of results obtained from an experiment to determine the relationship between the voltage and current through a metallic conductor. So we have a table here showing us the values that were obtained from an experiment to determine the relationship between voltage and current through a, take note, metallic. So it means when you are asked to draw a graph, I don't expect you to draw a curve or you draw with freehand. No, you are supposed to draw a straight line using a ruler. If the points don't seem to be falling along the straight line, draw a best fit line like I just explained. Okay, so we have our table of values here, and you are supposed to use these values to draw a graph. Now, what type of graph are you going to draw? So plot a graph of voltage. Let me see, I think there was a mistake here. This one was A, this is B, so this one cannot be A again. This one is supposed to be Roman numeral 1, and this one is supposed to be Roman numeral 2. Okay, so 1, plot a graph of voltage against current, and you get yourself 3 marks for doing that. Procedure is exactly what we have discussed in our lesson. Then the next question is, calculate the resistance of the metallic conductor. So the resistance of the metallic conductor, how are you going to calculate it? Remember what we have said in this point here, where we have said we can therefore conclude that the gradient of the graph is equivalent to the resistance of the conductor. So that's what you can see, that these points are very important, because it is from there that those questions were made. Okay, so I am going to post an assignment for you, and in this assignment I'm going to post, it is not going to be on a metallic conductor, it will be about a filament of a light bulb. So a filament of a light bulb, you have already seen in this lesson that it is non-ohmic, so you don't expect to have a straight line. So in that case, you will connect all the dots, drawing a smooth curve. Okay, so we've come to the end of our presentation. Thank you so much for paying your attention up to the end. Please make sure you do the exercise like I have said, and the assignment that will follow. So the same lesson has been posted on our Facebook page, which is NTC. To access it, follow the link below, which is at NTC Exam Coaching. The assignment I'm talking about will also be posted on the same platform. Thank you so much. See you in our next lesson, where I'll be talking about circuits.